Hello everyone and welcome back. Today we'll be continuing with chapter 3 and we'll be building a CNN to distinguish between horses and humans. So before going on, let me tell you one thing that this dataset of horses and humans is created by computer graphics and not by real humans and horses. So let's get started. Firstly, about the dataset. Our dataset contains 1000 plus images of 300 cross 300 pixel size. That's approximately half each of horses and humans. And they are of course in different poses. So as you can see here, here's a figure 3-7 where you can see different poses of humans and horses. As you can see, the subject have different orientations and poses and image composition varies. So consider the two horses. For example, their heads are oriented differently and one is zoomed out while the other one is zoomed in. So in this picture, you can see that one of the horses on the right has been zoomed in while the other picture of the horse in the left has been zoomed out. So now let's read furthermore. Similarly, the humans are lit differently, have different skin tones and are posed differently. So we can see that both of these humans as well as horses have different poses. That see one of the humans, the lady, she's standing by the sea, while the human, the man, is standing in a desert or a sandy place. Both have different complexions, different postures. So there is a wide range of postures in the dataset. The images also contain backgrounds such as trees, beaches, and so a classifier will have to determine which part of the image are important features that determine what makes a horse, a human, without being affected by the background. So what we were doing in the previous datasets, that the dataset that we had earlier, the images were focused in center. So there was no such background like plain background, no such background like oceans or sandy area or trees. But in this dataset, we have to find out the important features of the image and also determine what makes a horse and a human. While the previous examples of predicting y is equals to 2x minus 1 or classifying small monochrome image of clothing might have been possible with traditional coding, it's clear that this is far more difficult and you are crossing the line into where machine learning is essential to solve a problem. An interesting side note is that these images are computer generated. As I've told you before, the theory is that features spotted in a CGI image, that is computer generated image of a horse, should apply to a real image. So the CGI or computer generated images should look like or should have features that a real image has. In this, we'll be using the Keras image data generator. So what will it do? Let's read forward. The fashion MNIST dataset that you've been using up to this point comes with labels. Every image file has an associated file with label details. Many image-based datasets do not have this, and horses or humans is no exception. Instead of labels, the images are sorted into subdirectories of each type. So what it's telling you is that image file has been associated with the file with the label details. But the datasets, there are many datasets actually that do not have this. So there will be many raw datasets that don't have a label details. And maybe horses or humans is no exception. But the labels, instead of labels, the images are sorted into subdirectories. So there will be a main parent directory and under that there will be two subdirectories, one in name of horses and the other in name of humans. With Keras in TensorFlow, a tool called the image data generator can use this structure to automatically assign labels to images. So we'll be using data image generator to assign labels to images from the subdirectories. Now, to ensure that your directory structure has a set of named subdirectories with each subdirectory being a label. So what it's saying that each of the subdirectory is being a label in itself. So for example, horses or humans dataset is available as a set of zip files, one with training data and another with validation data. So training data is about 1000 plus images, while the validation data is 256 images. And if you're thinking that why we are just dividing it into training data and validation data instead of test data, we'll be understanding it in a bit. When you download and unpack them into a local directory for training and validation, ensure that they are in a file structure like the one in the figure we'll be seeing then. So the code here to get those subdirectory and the training data, to extract actually training data into appropriate subdirectories is shown here. So first you use urllib.request for making a URL request to get that library, that parent library. Then we have to import zip file to open and close the file. Then here is a URL that we have to use. You can just copy paste it. I'll give you the code in the GitHub only. Then we have the file name of horse or human.zip, the training directory, so horse or human / training. Then we use urllib.request to retrieve the URL, file name. So we'll retrieve this file. Then we'll read the zip file using zipfile.zip file, and then we'll extract all the training data, and finally we'll close the zip file. So here is the image that will make you understand this better. So the asset structure says, first we have images parent directory, then there are two subdirectories, one in name of training data and second in name of validation. So training and validation then have two subdirectories in name of horses and humans. This simply downloads the zip of the training data and unzips it into a directory at horse or human / training. The parent directory is the same as training, validation, and its parent directory is images. To use the image data generator, we now simply use following code. So what we are doing here is we are using from tensorflow.keras.preprocessing.image, we'll import image data generator. So we'll rescale all the images by 255, dividing by 255, and using train generator as a directory name. So use train datagen.flow from directory. So we'll be getting the data in training directory. The target size is 300 by 300. Class mode is binary. First, we create an instance of an image data generator. So train underscore datagen is a instance of image data generator. We then specify that this will generate images for the training process by following or flowing them through the directory. So what does it say is that we specify that this will generate images for training process. So we'll generate images for training process that will flow through a directory, that is training directory. So all the training data or images will go directly into training directory. So also along with that, we have some hyperparameters about the data such as target size and the class mode. So what are hyperparameters is the parameters that do not change while training the model. So the size of the image in this case is 300 by 300, and the class mode is binary because we are just categorizing whether the image we have got is of a human or a horse. So we are using a binary class mode. Next, we'll understand the CNN architecture for horses or humans. So we'll take into account when designing an architecture for classifying images. So things that you should take into account are First, the image size is quite large. So earlier we were using smaller image sizes, but now the image size is 300 cross 300 pixels. So it's way more large. So that means that we'll be needing more layers. Secondly, earlier we were using grayscale images or monoscale images. So that's why the channel used to be 1. So remember we were writing 300, 300, 1 for one channel. Now we'll be writing 300, 300, 3 for 3 channels because the image is colored, that is RGB for 3 channels. Third, that there are only 2 types, image types. So one is horse and the other one is human. So that's why on the output, we just need a single neuron. Because if the value of neuron is 0, means it's class 0. If the value of neuron is 1, it means it's class 1. So it's easy to classify. That's why we need only one output neuron. So here is the model. First, we have all same as it is, but we have just increased the number of layers because of the image size is greater. So we have defined con 2D with 16 convolutions. 3, 3 is the size of the kernel. Then activation is ReLU, and you can see the input shape is 300 by 300, 3 for RGB. Then we have used a max pooling layer for 2, 2 the shape of the filter. And similarly, we have copied from con 2D and max pooling a couple of times. Let's count to like 4 or 5 times. 5 times it is. And finally, then we flatten the layer, we give it to the dense, and as in the output you can see for the last layer there is only one neuron. That means that we have a output 0 or 1. We only need output 0 and 1, and that's why we have also used a activation function called sigmoid, which can very well differentiate between zeros and 1. So we are defining 16 filters for convolution layer, each 3 cross 3, but the input shape of image is 300, 300, 3 because it's a RGB image. So that's why we've already discussed that. At the other end, notice that only one neuron in the output layer. This is because we are using binary classifier, and we can get a binary classification with just a single neuron if we activate it with the sigmoid function. So what does the sigmoid function does? The sigmoid function is used to drive one set of values towards 0 and the other towards 1, which is perfect for binary classification. Next, notice how we stack the several number of convolution layers. We do this because the image size is quite large and we want over time to have many small images, each with features highlighted. So let's do model.summary. Here's a model.summary as before we have done in previously. Now for con 2D we have parameters 448. Then for max pooling there are no parameters because it's just getting the maximum value from each pool and making another array. Then for the last one you can see that for last convolution there is a big value. And let's move on to the next one. Yeah, for the second last dense layer you can see so many number of parameters, and for the second last and the last one you can see that there is only one neuron along with none, 1 and 513 parameters. But we can see that total number of parameters is way more than for the previous model that we have already done. So note how by the time the data has gone through all the convolutions, pooling layer, it ends up as 7 cross 7 items. So let's go back and check that the size of the data. Earlier it was, from the starting we go, the data was like 298 cross 298, 16. Then coming down to convolution second, it's 147, 147. Then coming down to third convolution, it's 71, 71. Coming down to another convolution, it's 33, 33. And coming down to another convolution, it's 14, 14. But finally, after max pooling, the size is 7 cross 7. So we can see the image size has reduced from 300 cross 300 to 7 cross 7. Feature maps is the word for that. So what the feature map is exactly? Feature maps that are relatively simple, containing just 49 pixels, so that's 7 times 7. These feature maps can be then passed to dense neural networks to match them to the appropriate labels. Now let's read ahead. To train the network, we'll have to compile it with the loss function and an optimizer. So what we have done earlier is we have used lots of optimizer and loss functions. So in this we'll be using binary cross entropy cross loss function, because there is only two classes. So binary cross entropy will work because binary is 0 and 1, and as the name suggests, this is the loss function. But we'll be using a new optimizer, that is root mean square propagation, and we'll be giving it a learning rate parameter as well. So we are using RMS prop as optimizer. So model.compile gives loss with binary cross entropy, optimizer as RMS prop with learning rate of 0.001, and matrix same as accuracy. And finally we can use model history equals to model.fit, and it's okay if you don't use model.fit underscore generator. Instead you can just use model.fit, then pass on the train generator and the number of epochs. So there is one thing, that if you are not working in Colab, you are running it on this code in your machine, so please ensure that pillow libraries are installed using pip install pillow. Then note that TensorFlow keras you can use model.fit easily, as I have told you earlier. Just over 15 epochs, you will see that architecture will give you around 95% accuracy on the training set. Validation set, for that we'll see this again. We'll follow the same procedure as we have done for the training set. So for simple models, there's a note. For simple models like the previous one, it's sufficient for that data set is divided into two parts, that's training and testing. But we will understand why we separated this data set into validation and not training and test sets. So understand what is training data. Training data is a data that is used to teach the network how the data and labels fit together. So training data means is just teaching the machine. Then validation data is to check if the network is doing with previously unseen data, how the network is doing with the previously unseen data while you are training. So it's like you've learned something, you are in the process of learning, and you are just checking your knowledge by trying out few examples, but you haven't learned that thing fully. So your previously unseen data while you are training, that is, it isn't used for fitting data to labels but to inspect how well fitting is going. Test data is used after training to see how the network does with the data it has never seen before. Some datasets come with three-way split. In the other cases, you will always want to separate the data into test sets. So two-part testing you can do, or you can simply divide the test data into validation and test set. So the code is same for validation as well. So as we have already seen, this code has been same as the training one. There is no much difference to it. Now simply we have the validation data. Now we have rescaled it, we got the data in validation directory, we set the target size, we have the class mode as binary, and we now have to do is we just need to put history equals model.fit, pass in the train generator, pass in the number of epochs, and run it with validation data equals validation generator, right? So when this runs, the validation accuracy comes out to be 88. So what does it mean? That the model has overfitted. That means that If the training accuracy is so good, that means that the model has learned the data very well. And on the validation accuracy is low, means that it has not been able to generalize it that well that we wanted it to. So the performance isn't bad considering how few images it was trained on, but we can of course work on it. You're beginning to hit a wall caused by lack of data, but there are some techniques that you can use to improve your model's performance. So now we'll test it. We now need the test data. So what will we do to test it is, the author gives a story of himself that a major frustration of his is when I was starting my AI journey was that I could find lots of code that showed me how to build models and charts of how those models were performing, but very rarely was there a code to help me kick the tires of the model myself to try it out. So testing the model is perhaps the easiest using Colab, as he says. So what we are going to do is we're gonna run the model. For that, what he's done is he's got a few pictures of horses and humans on Pixpay. That's royalty-free website, so you can always give it a try. Now, then what we do is we get few images of humans, like you can see two girls and a horse, and we'll try and ask our model to classify that. So let's just jump to the code ourselves. So here's the code that you first import NumPy, and from Google Colab get import files. From keras.preprocessing import image, and uploaded files.upload. So the code is here that for fn and uploaded.keys, this is the path where the images will be stored. So image.load image path, the target size, and as we can see that the target size here is 300, 300 because the images that we get from the net can have any size. So, but our model is used to getting 300, 300 as the size. So that's why we have set the image target size as 300, 300, but the image is a form of and normal image pixels, but we have to convert it into an array. So that's why we have used the next line, that is image.image underscore to underscore array. And then what we have seen here is that our model is trained on three channel image, right? That's 300, 300, 3. But this is only one dimension with no dimensions, at least 300, 300. So we are using NumPy for NumPy.expand to expand the dimensions. And finally, we stack these layers, this whole image together. And finally, we use model.predict on the image and print the class. First, when we have the class, we'll print the class. But if the size of the class or the output is greater than 0.5, we'll say it's a human, else we'll say it's a horse, as you can see. When you'll run this, you'll understand this better, but let's just read through what each of line of this code tells us. So you can also upload images simultaneously and have model make predictions for all of them. You may notice that it tends to overfit towards horses if the human isn't fully posed. That is, you can't see their body, full body, it can skew towards horses. So you will see yourself when you will actually run through it. But first we'll just look through the code that we've already just have the look at. So what was the code? That image equals to image.load image, give the path and the target size. We are loading the image from the path that Colab wrote it into. So when we downloaded the image or uploaded the image, it went to the path. So we are loading the image from the path that Colab wrote it into and specify the target size to be this. So we are reshaping the size of the image that we have uploaded to the actual size that the model takes as input. The images being uploaded can be any shape, but if we are going to feed them into the model, they must be 300 cross 300 because that's the size of the model was trained to recognize. So the first line of code, loads the image and resizes it into 300 cross 300. The next line code converts the image into a 2D array. The model, however, expects a 3D array that as indicated by the input shape in the model architecture. Fortunately, NumPy provides us expand dems underscore dems method that handles this and allows us to easily add a new dimension to the array. So we had a single dimension of image, then we used NumPy to convert it into a 3D array as it's required for the input to the model. Now that we have our image in 3D, we just want to make sure that it is stacked vertically. So we use np.vstack, so stack vertically, and predict, model.predict. Model returns an array containing the classification. So we get an array for the classification. Because there is only one classification in this case, it's effectively an array containing an array. So you will see this in where for the first human model, it looks like this. So let's see the figure. Yeah. So let's see that there was 3 images uploaded. First was the model, second one was beautiful, maybe a girl, and third is a horse. So what's the output of the model? That first, for the model image, it says it's a human. So 1 dot. For 0, it means it's a horse, but it was actually a girl. So that's wrong prediction. And for third, it was 0. That means it's a horse. So from that, we can say that 0 means horse and 1 means human. Now, moving on, we can say that if the greater value is greater than 0.5, we are looking at a human. If it's less than that, we are looking at a horse. There are a few important points to consider here. First, even though the network was trained on synthetic computer-generated imagery, it performs quite well at spotting horses or humans in real photographs. So it does a pretty good job. Not we can say that it did accurately understood what was a human or a horse, but it did a pretty good job. This is potential boon in that you may not need thousands of photographs to train a model and can do it relatively cheaply with CGI. So that's a benefit of CGI, that you really won't need lots and lots of images, or won't need the time to spend on clicking so many images or collecting data of so many images. But this dataset will also demonstrate a fundamental issue you will face, that is, your training set cannot hope to represent every possible scenario of your model might face in the wild, and thus model will always have some level of over specialization towards the training set. A clear simple example of that was shown here, where human in the center of was miscategorized. So there was a girl with the hair on her hair was falling on her face, and it was actually misclassified as a horse. The training set didn't include a human in that pose, and thus the model didn't learn that a human could look like that. As a result, there was every chance it might see the figure as a horse, and in this case it did. So what's the solution to this? So obvious one is that you need to add more data so that it can classify well between humans and horses. So first was that isn't always possible, and we know that if you need lots and lots of data of humans and horses, it's really not a good idea to get a lot of data, and sometimes you can actually never get a lot of data. So that's one thing. But the second thing that you can actually do is image augmentation, that we'll be exploring next. So we'll just go through the code of this chapter, that humans and horse classification, and I've already run this code before because it will take a lot of time to rerun it, because the training of convolutional neural network actually takes a long time, because the dimension of the image is big, as well as there are a number of layers. So let's jump to the code right away. So you have already seen the coding this collaboratory before chapter 3, and I'll be continuing with this only because this code belongs to chapter 3 only. So as I've done this is I've just imported url lib.request and zip file because I need to access the zip file. So this was the URL. You can easily get all this code on the GitHub, and I'll link it in the video also. Then the file name horse or human.zip. Then you download the training data in horse or human slash training slash url lib.request.url retrieve to retrieve the from the URL you're retrieving the data as well as the whole files. Then you get referring or reading the zip file that you receive and extract all the training data, and finally you close that zip file. So it's very important for in case of files that you open it well in read or write format as anything as you want, and it's very important to you always close those files because it can actually change the whole content of the file. So the training data is 1000 plus images of 300 cross 300 pixels, while the validation data is around 256 images of 300 cross 300 pixels. So first we'll be dealing with our training data. As we have already understood this, we'll be using image data generator, using keras preprocessing.image. We are rescaling the image as we've done before, and we are just putting those images into training directory, having a target size of 300 cross 300 and the class mode of binary. So as you can see, the output comes as found 100,027 images belonging to two classes. There are only two classes. Then I've got this imports again because I was running this. So I've written the model here. The architecture is here. We need more layers because the image size was large. Then the image are colored, so there are 3 channels. So the image size would be, input shape would be 300, 300, 3. And the binary classification means we need only 1 neuron in the last so that we can get 0 or 1 for each class. So we already discussed this whole model. I don't think we need to discuss that again. And model summary, we have already seen the output shape and the number of parameters here, and how the size has decreased from 298 to 7 cross 7. And finally, our last layer having only 1 neuron and the total number of parameters that's are trainable. Then we compile the model simply using binary cross entropy because it's a binary classification. Then using optimizer tf.keras.optimizer.rmsprop. So if you ever face any problem of running rmsprop, just use this before rmsprop and it will run fine. And the metrics is accuracy. Then we get model.fit with train generator and number of epochs equals 15. And you can already see that around this I got the accuracy of 99 to 97% on the 7th epoch, and then it's just 1 accuracy is like 100%. Then moving on to the validation set, you just get the validation data as the training data, same code goes in, just the change of this. Then we have validation data generator, image data generator for validation directory, and the binary class mode. So it says there are 256 images belonging to 2 classes for the validation set. Then you just simply fit it for 15 epochs. Then you get the accuracy of validation accuracy. As you can see, it's around 80%, not actually 88 that was given in the book. It's around 80%. And for that we can say that the model is overfitting. So let's test our training images, test images. So just imported NumPy, google.colab import files, got the image, uploaded it. So these were 3 images that I used. So first one was a horse. This HU1 was actually a human, it misclassified it as a horse, and the last one was actually human and it said it's a human only. So yeah, the model as we have read in the theory It works the kind of same, that it's overfitting. And next we'll be understanding how image augmentation can help us with that. But before that going, you can actually check out this whole code on GitHub, and I'll be dropping this code in the GitHub just recently. And also you can get the link to this code in the description. Do check it out, and if you have any queries or any questions, do drop it in the comment section. Thank you so much, and see you next time.